Okay, so now we're going to be taking a look at vectors. Excuse me there. So we'll be taking a look at vectors. Now, vectors are kind of a complicated subject, but for our purposes, all we really need to think about a vector is as a combination of a magnitude and a direction. And so we can go ahead and represent a vector by drawing an arrow, and the length of the vector will give us the magnitude, and the directions pointing gives us, well, the direction. Now we should probably give the vector a name, so let's call it A. I don't know what it represents yet. This is just a generic vector. Notice here that I put a little funky half arrow over the letter A. When you're handwriting, that's usually how you denote that you're writing a vector. Now your book will go ahead and instead write the letter A in boldface. That's kind of a common notation. Now the magnitude of A, just plain its length, you write as A without the little arrow over it, or the way your book will do it is it'll write it in italics. Okay. Now, we can also choose instead to represent a vector as an ordered triplet of values, which we call the components of the vector. So ax, ay, az. This represents the piece of A in the x direction, the y direction, and the z direction respectively. And if it's positive, it's pointing in the positive x. If it's negative, it's pointing in the negative x, and so forth. Now, when we're testing for equality of vectors, we're testing for equality of vectors. If we want our vector A to be equal to our vector B, there's two ways we can do it. One is we can demand that the components individually be equal, so ax equals bx, ay equals by, az equals bz, and so forth. If we're comparing it graphically, say this is my vector A, and this is my vector B over here. What we need to have happen is what's called a parallel transport. If I can slide my vector A so it sits on top of my vector B without changing the direction it's pointing or changing its length, if I can get the two to sit right on top of each other, then we say that they're equal. Okay. Now when we're adding vectors, again, if we're doing, it by components, say I want my vector C to be equal to the sum of my vector A plus my vector B, like so. One way I can do that is to add up the coordinates. And the way you do this is what I call slot-wise. You add the first two slots and the second two slots and then the last two slots and so forth. So this will give you ax plus bx, comma, ay plus by, comma, az plus bz, and so forth. If you're doing it graphically, there are two equally equivalent ways of doing it. I can go ahead and put the tail of my vector b onto the head of my vector a, and then the sum of the two is what I get when I connect the tail of a to the head of b. So it's a plus b, like so. We usually call this the tail to head rule because I put the tail of b onto head of a, and then the answer goes from tail of a to head of b. So you go tail, head, tail, head. We can also do it by what's called the parallelogram rule. What I can do there is I can put in my vector a like so, my vector b like so, and then I imaginarily complete the parallelogram, and that would be my vector sum a plus b. Okay. One of the other operations I can do is I can multiply by a scalar. A scalar is just a fancy way of saying just a number, no direction. So I can take some scalar c and multiply it by a. Again, if we're doing it in components, say x, a y, a z, I multiply c by each of these individually. So this will be c a x, c a y, c a z, like so. If I'm doing it with arrows, I go ahead, I take my vector a to a, would be one twice as long, pointing in the same direction. Negative a would point in the opposite direction. We usually say it points anti-parallel. And I can combine the two ideas and say that negative 2a points anti-parallel and is twice as long. This leads into vector subtraction. And I only ever teach one way to do it, and that's to add the negative. There is such a thing as the head-to-head rule, but I find that works better for people to figure that out for themselves. So we'll start again by doing it by components. So a minus b. This will be the same difference as a plus negative 1 times b. So if I was doing this slot-wise, this is going to work out to be ax minus bx, ay minus by, comma, az minus bz, and so forth. If I was doing it graphically, say this is my vector a, and that's my vector b, what I would do is I would add negative b to a, so there's a, there's negative b, like that, and then that gives me a plus negative b. Okay, we do also need to have some sort of additive identity. The additive identity gets called the null vector. Usually gets cleverly written as 0 with a little vector over it, and it is 0, 0, 0. There's no defined direction. You'll find a lot of books, they don't bother putting the little arrow over it. That's strictly speaking not correct, because without the arrow, that's just the number 0, and we would have to compare against 3 different numbers 0. So it's more correct to draw the little arrow over it, but I don't get strung out if people don't do that, because you'll see it all the time. Okay. So now let's go through and work through some of our identities with vectors. We'll start with the fact that addition commutes. And we'll do this just to give you some sort of flavor for how people actually prove these things. Usually it's easiest done in component form. So let's go take a look. A plus B. I'm going to assert that that equals B plus A, and it does. But let's go ahead and prove it. Oops. So we'll do it by just saying, well, does AX comma AY comma AZ plus BX comma BY comma BZ, does that equal the reverse? BX comma BY comma BZ plus the same thing with A's. Now, it would be tempting to just flip these two, but then you would have been assuming the truth of what you're trying to prove in order to prove it, and that'd be a bit of a no-no. So you actually have to go ahead and do the additions. So that will be our next step. AX plus BX, comma, AY plus BY, comma, AZ plus BZ. And we're still trying to figure out if that equals, okay, what do we have on the other side? There'll be BX plus AX plus AX, comma, BY plus AY, comma, BZ plus AZ. Okay. So I'll take another one of those there. And then what we can do is, even though I couldn't just flip these two here, I am allowed to flip the order of these because that's just scalar addition. We know that commutes. So we'll go and say that that's AX plus BX, comma, AY plus BY, comma, AZ plus BZ. And hey, term by term, they are all equal. And that completes the proof. Okay, other things that I'm not going to prove, but you can certainly do them for yourself. The idea is similar, is we get that addition does associate. So that means that A plus the quantity B plus C, oops, B plus C, that does indeed equal A plus the quantity A plus B plus C. And you prove that in the same kind of way that I just did. And scalar multiplication does distribute. Scalar multiplication distributes over vector addition. So the scalar C times the quantity A plus B, that is indeed equal to CA plus CB. Now be a little careful in your text. Equation 1.38 that refers to this does have a typo. This is correct. Okay, so we still need to define a few more things. So let's go ahead and do a better job of defining the magnitude of the vector. The magnitude of the vector is its length. So if you want, you can write that as the norm of A. And it obeys the Pythagorean theorem. So ax squared plus ay squared plus az squared, take the square root. Okay, we also have some very special vectors that get called the unit coordinate vectors, or just simply the unit vectors. These things go by a bunch of names. We'll follow what you've probably seen in calc. So this is x, y, z. This is a vector of length 1 along x. Now, if you're a good physicist, you should be busting my chops and saying 1 what? A number without a unit is worthless, and normally that'd be right. But here, this is just purely a vector of length 1 that points in the correct direction. If, say, I'm trying to construct a velocity vector, I'll have to multiply it by some quantity that has units of meters per second in order to make the units work out. Similarly, the unit vector that points in y gets called j hat, and the unit vector that points along z gets called k hat. These are, notice here that when I write the I and the j, I don't put a dot in them. That's pretty standard. The little hat kind of takes the place of the dot when you write it. So anyway, that means I hat is just equal to 1, 0, 0, no units. Some other notation you'll see, sometimes it's called EX or X hat. Similarly, J hat is 0, 1, 0, and it would be equal to EY or Y hat, and K hat is equal to 0, 0, 1. That would be equal to EZ or Z hat in other books. Okay. So we've so far seen how to multiply vectors by scalars. There are other ways of combining two vectors, but we'll make that the subject of the next video.